Hello, everyone, and welcome to the latest edition of zkStudyClub. Today, we're excited to welcome Dmitry Khovratovich of the Ethereum Foundation and Dusk, Pearson, formerly at Dusk and now at Polychain Capital, and Joshua Fitzgerald of Anoma. They're going to be presenting their work on reinforced concrete and Plonkup. Again, so we're really excited to have you guys, and over to you all.
Okay, cool. Hello, everyone. Glad to see that many people. So our talk will consist of two parts. So the first one will be more about the new reinforced concrete hash function and why it was fun to design it and probably should be cool to use. And the other part will be about Plookup integration into Plonk and the result in Plonkup, which will be delivered by Luke and Joshua. So I'll be the first, and the guys will be after me. So basically, we are two from a bit different teams, but this is sort of a collaborative work. And also the reinforced concrete itself, I forgot to mention that the first slide, but it's also a collaboration from a number of people, mainly from Technical University Graz in Austria, but also one person from Radboud University in Netherlands. So the paper is on e-print just in case, but yeah, let's go into these slides. So basically, this will be the entire slide set, and the first part will be about reinforced concrete. The second about Plonkup. Plonkup is just kind of a portmanteau of words for Plonk and Plookup. And basically, let's look into the first part then. So this table that you see on the first slide is intentionally imprecise, but what it should kind of provoke is the great disparity between the existing hash functions. And in this table, we have three important columns. So one column is the first one. The first one is the name of a hash function, and the second one is about the time that is needed to prove a statement about this hash function in zk, which is more or less approximated by the number of gates in the proof system you are using. The third column is the time that you need to compute this function on a regular CPU in the native mode when you just have to compute the hash. And the fourth column is the amount of cryptanalysis that has been invested into this hash function. And basically, the more the better. So what the disparity is, it's that in the zk mode, the fastest are Poseidon and Rescue, but in terms of number of gates, so they're the fastest, but they are also the least explored from cryptanalytic point of view. The more traditional hash functions like Blake2 have enjoyed a good amount of cryptanalysis since designed 10 years ago, but they are much slower in zk, even though they're terribly fast in regular computation, so just a few cycles per byte. And the fourth entry in this table, so-called Pearson hash, which is just basically a sum of elliptic curve points with coefficients from the pre-image bit string. It's rather fast in zk and is reduced to well-tested assumption, kind of untractable problem of discrete log. So I've given it the greatest mark in cryptanalysis, but in terms of evaluating on x86, it's also kind of slow. So the natural goal in the design of such hash function is to do something which is ideally fast, both in zk and on regular CPU, and could have enjoyed already good amount of cryptanalysis by inheriting some design principles which have been well tested in the past. And one possible application, for example, of such a function is its usage in zero-knowledge schemes where you do have to compute big Merkle trees over the course of your prover, such as, for example, recursive schemes, where during the recursion you have to build a full tree over a witness, and then when you basically the next step of recursion is to prove a statement about this Merkle tree. This is usually fast, but building a tree is not fast. And if you want that the proving the witness is fast, then a tree should be built upon a zk-friendly hash function. And then if a zk hash function is slow on CPU, then it becomes a bottleneck. So we want something that is fast, friendly, and long-term tested, which seem to be kind of a not easily achievable goal, but I think we have approached it to some extent. So, and when we clearly understood what we wanted to achieve, we turned into two possible ways to construct a hash function. Basically, there have been two ways. So one option is to use some compression function, which is non-invertible by design, and is built either on some core non-invertible function like SHA-2 or some well-tested assumption like Pearson hash, which is built on the complexity of discrete log. So it just adds elliptic curve points inside. And the second option is a so-called sponge framework, which is built on an invertible transformation, or also called permutation. So it doesn't permute element, but it's just a biject. And examples of such hash function are Ketchak or SHA-3, Poseidon, Rescue, and actually a lot of other designs, which are also SHA-3 finalists, for example. So we have chosen the second one because it seems that in terms of performance, we kind of exhausted the first option. And if we wanted to have, if we wanted a sponge, we need some kind of a mapping. For it to be a sponge, we need a mapping from basically tuples of field elements into tuples of field elements. So in order to have a compression out of it, we will just truncate. In the simplest case, we'll just truncate one output element. So and constrain one input element. So technically, to make a non-invertible function out of it is technically simple. So as long as you have an invertible transformation which doesn't exhibit any non-trivial behavior or invariance, it can serve as a good hash function. And actually, indeed, what you just need to create a hash function is this sort of transformation, big F. If you have good big F, you'll have a good hash function. And it's fairly invertible. You just have to find a way to construct such a function which is fast and has few constraints or few gates in application, stuff like this. So a typical approach in hash function design is to make this F as a composition of smaller Fs. And the small F is usually called a round. And up to very recently, like for example, Poseidon and Rescue and some other designs, that each round has just a compact algebraic description, which in terms of zk proof systems is usually a low degree polynomial over the state. So basically over a triple, for example, in our case, the simplest case, the triple can be more field elements. We need many rounds because what we want eventually is that the degree of the entire transformation F is sufficiently high, but also that if we compose a system of equations based on this round function descriptions, then such systems should not have what is called Grobner basis of low degree. And because of that, we need more rounds. And this number of rounds, this big number of rounds made all the functions rather slow, because if you had high degree here, then it would be slow in zk. If you have low degree here, then you need many rounds to accumulate degree over the entire function, and because of that, this kind of multiple rounds makes you compute a number of multiplications over the finite field, which for the majority of fields used in practice can be sufficiently slow. So we want somehow to break this circle that makes us to create a function with many rounds. And what we did, we decided to choose a very, very different round function, which hasn't been used before. And for this, it's not a spoiler that we used the power of Plookup, well, the ability to have gates based on lookup tables. So for round function, there can be many different round functions that we have seen in hash or block cipher designs, and we can also evaluate them from the perspective of a prover, meaning how expensive it would be for a prover to go over all the constraints for such round function. We can look at the evaluator who computes it on x86, and we can look at the cryptanalyst. So multiplication and addition is very fast for prover or evaluator, well, rather fast. But from cryptanalytic point of view, is this quality is low, we need many such functions. If you have a field roots like a big exponent in the field, then it's good for a prover but slow for an evaluator. That's the rescue hash function case. From cryptanalytic point of view, it's better than just multiplication addition, but not sufficiently better because you still have to accumulate high degree. If you use Pearson, then this means that for round function you choose the elliptic curve point addition, and this makes the prover also a bit more expensive because elliptic curve addition is not for free. You have to use several multiplications to do the point addition. And from the evaluator point of view, it's also kind of slower because you do these additions over the field. From cryptanalytic point of view, it's all perfect. If we look into block ciphers, then we'd have S box in the AES block cipher. Here S box is a mapping byte to byte in the case of AES. In the prover, for the prover, this is expensive. It was expensive till the Lookup, but for the evaluator point of view, it's quite fast. So having a lookup table on a small table of 256 elements is definitely fast. It fits into a cache. Everything is fine except for some timing attacks. So for cryptanalysis point of view, it's almost perfect except for this timing attack. Stuff like arithmetic that you use in SHA-2 or SHA-3, like bit twiddling stuff, it's really bad for prover, but good for evaluator because it's just bit operations. From cryptanalytic point of view, it's also well explored. So you see that no round function has pluses in all columns, but we want something that has plus in all columns, and that's the new round function that we call bar. Actually, the bar is the essence of the reinforced concrete. After we had designed bar, the rest was purely technical, and this is actually the main and the most important point of the design. So if you understand how bar and why bar, you got like 90% of reinforced concrete. So let's look what the bar is. Well, a short remark why we didn't consider Pearson or its recent design kind of evolution since Emilia. Well, first of all, please excuse me if I make a bit of mistakes here because I've not studied since like in 100% detail in the constraints that the guys at Zcash plan to use it. But the thing is, if you look into the hash function that is just addition of elliptic curve points, then the problem is that the result is homomorphic, and the field multiplications that you are doing here is still slow, even if these are not just separate bit but bit strings. And also decompositions into bit strings is rather expensive. And actually what we do in the design of bar, we do this decomposition actually faster than before, but we also combine this decomposition into some other transformation. It can be interesting actually. So maybe in the future we can have some combination of these two approaches and have something even better from the security point of view. I wouldn't exclude it. So yeah, in the design of bar, we need high algebraic degree to prevent all algebraic attacks. we need it to be friendly, and we need it to have high performance on x86. How to achieve it if we have the power of Plonk and Plookup tables? I don't have to look into how exactly Plookup works and how it's used together with Plonk. That's the title of talk by Luke and Joshua. I just need the fact that there are tables that I can check, that there are kind of wires that I can check that they are present in some tables. That's the only thing I need. So why we have to put so much effort in? If we were not in the field, the situation would be much better, because in the standard approach from x86, if we we work on like n-bit strings, and we can simply do just split it into whatever we call them, bytes, chunks, words, buckets, and then you apply some high degree function just bucket wise, and then you combine it back and apply some, I don't know, bit diffusion, like permutation of the bits or something, and it gives you high degree because this guy is high degree, and it gives you resistance to majority of attacks because usually high degree function is secure against many attacks. And the crucial feature here, why this is possible on x86, because the domain we work is separable into subdomains. It can be represented as a product of subdomains, which can be, and elements from the subdomains can be modified arbitrarily. When you combine them back, it's always a valid string again. So if f is a bijection, then when you combine it back, it's again a bit string, which is a valid. But it's an n-bit string. So this n is different. Sorry. But as we are in the field, the station is much worse. And I'll give here an example. So after the example, there will be a much more technical part, which I'm going to skip for the talk, but it can be easily looked up later because the slides will be shared. So suppose that we work modulo some prime, and this prime is, for example, 769, and in hexadecimal is just 301. We can't really just split it into three 4-bit words and transform them arbitrarily, because if we split it like this, then we just can't apply arbitrary f here, because the result may overflow. So suppose you take like p-1 as an entry you want to modify, it will be 300, but then this means that the last zero you can't transform to anything, because if you have 300 and if these guys remain 3 and 0, and if you transform the last digit into anything, it will overflow. So if you want this transformation to be independent, then basically for the vast majority of cases it must be a fixed point. So f must be a fixed point for this case if you do such a division, and this clearly won't work for us in terms of security. So what we want is to find a way how to split a field element into something that is not bits or bit strings. And this actually the most non-trivial thing. What we do is to look as we took a bit different decomposition here. Look that 769 is smaller than 775, which is a product of two numbers. They don't have to be prime, they just have to be some numbers, so that when I can kind of embed fp into the product of integer domains, and then I can represent any number in fp as an element from this domain by simply taking it, for example, modulo 25, and this will be the last element, the second element of the pair, and then if I subtract it and divide by 25, it will give me the first element of the pair. So the p-1 will be 30 and 19 in this representation. What it gives me, it actually gives me quite some power, because I can now, if I if I split the filled elements into two integers, one smaller than 31, the second smaller than 25, then I can transform them almost independently and transform it in a way that the result has high algebraic degree. So suppose that S is a transformation that has fixed points for X being 20 or bigger. So from 20 to 30, but everything that is below 19, from 0 to 18, it can be arbitrary. It can be very high degree, can be of degree 18 or 19. So, and then I can make the following transformation. So if I represent my X as 25 times X1 plus X2, so that X1 is smaller than 31 and X2 is smaller than 25, and if I require that the only thing that I require for it to not overflow is that if X1 is maximum possible, 30, then X2 must be smaller than 20. And if these rules are satisfied, then I can transform X1 to Y1 and X2 to Y2. And as a result, I have another element from the domain from this, actually the product of two domains. And when I combine them back, I have a bijection. This is actually the main non-trivial statement that we have here also as a theorem for bigger decomposition in the paper. But it's of utmost importance to understand why it works, because what I want to exploit is that these rules I can encode as lookups, and actually just a few lookups. And these lookups, actually, I will combine with these lookups later on. But the most important thing is that this makes a bijection. So whenever X1, X2, Y2, Y1, Y2 satisfy these rules, then there will be no overflow. There can be no collisions. There can be no two witnesses corresponding to the same field elements X and Y. Are there any questions at this point? Okay, no. Then basically what it remains is to generalize this approach into something that looks there like a bit scary. But the idea here is that instead of separating a prime into two elements, we separate them into n elements. So this can be seen as an expansion with variable base. So if you have like a decimal base, then this b is 10 in all the, it's just powers of 10. If it's binary, it's powers of 2. But in our case, the base, all the bases are different, and we have such decomposition basically. So each element X we represent as a tuple of n elements, so that they determined uniquely. And under certain rules, they are assembled back into field elements with no overflow. And this S1 and so on Sn are chosen so that for p minus 1, there is this values x1, x2, xn minus 1, and xn have certain property. So there is some sophisticated algorithm that search for this decomposition. So not every set of numbers is good enough. So yes, and yeah, this is kind of a technical part I want to go over rather briefly. So the thing is, in here I didn't say what S is, but in in the case of many field elements, in the case of decomposition into the product of many domains, this S is of high degree, and this is chosen in a certain way so that F has the resultant so-called S box has high degree. I skip over some text intentionally because it would be better, I think, to look at this offline. So I would like only to emphasize one thing. So first of all, that the resultant construction is a bijection for which you have a long theorem. And in terms of performance, it can be computed with n modular reductions over small numbers. So every modular reduction is over some number which is smaller than 700. In our case, we have 27 reductions. It can be computed with n table lookups and n array integer addition. And this is to compute the function. So 27 reductions modulo small numbers, 27 lookups, and one combination back of these elements into a single number. That's for x86, why it's fast enough, because we can make this n actually small, rather even smaller. And in terms of constraints, if we use table lookups from Plookup, then basically what is possible here is that we can ensure this transformation without overflows that I mentioned for the small prime use case. I can ensure this transformation with rather small number of lookups and constraints. So actually, I have two additions, like these guys add together to field element, and these guys add together to field element. But apart from that, I need only a few lookups. So I need a lookup for this, but the non-overflow constraints, they don't give me a big overhead. So actually what I have here, so if I have 27 buckets, then I have 27 constraints which have inside this nonlinear transformation I had mentioned, but also I can handle overflows. And if we should care about overflows or we shouldn't care about overflows, some sort of a carry flag, then I managed to put everything into a single lookup constraint with some additional table lookups to ensure that these carry bits are actually 0, 1, 2, something like this. And so that I can have 1.6 n table lookups. So what it means in terms of concrete numbers, it means that in order to hash two elements from the big primes from the field, the natural field like BLS field or BN254 field, I need just 126 table lookups to hash two elements. And the table, the big table that I use is 1,500 entries, plus some additions and multiplications, but not terribly many of them. So I think in total, if you count in like Plonk gates, then it'll be 100 more gates to handle some additions here, because also in reinforced concrete, there are some extra layers that ensure the resistance to traditional attacks. But the main kind of improvement, kind of innovation that we use here is indeed this decomposition and a set of constraints that we come up, so that altogether we need kind of close to minimal number of lookups in order to have together the decomposition, the composition, and a nonlinear transformation.
Dmitry, I have a quick question, actually, too. I think just to clarify on for the C constraint at the 0, 1, 2, I think I'm assuming that means, you know, the three possibilities are to handle no carry, an underflow, or an overflow. Is that right?
Yes, yes. So if basically when you have your decomposition of a field into many buckets, then you look from them from highest to to lowest, and then you compare each bucket to the highest possible value. So while it's still highest possible, you have to check that kind of next one doesn't overflow. But if at some point you're below the highest possible, then the rest can be arbitrary. And this station you kind of carry. So it's like a finite automaton when you check over the carries from highest bit to lowest bit.
Yeah.
Like this.
Got it. And then can you go, maybe I missed it, but can you talk about, I think, the Z? So what is Z defined as in this slide? I think you mentioned it. Can you go?
Yes. Well, this is a bit technical. So the Z's are, because I want the same transformation S for all the buckets, but the buckets are of different size. And what I need with Z is that basically it allows me to use the same S, but for different buckets. So I kind of can have the prefix, the first 600 of elements, first 600 of S, the outputs of S, common to all the buckets, so they don't multiply. So they kind of, every bucket has 600 elements, but the final table is not 700 times 27, because for the buckets they kind of share this value, and in order for them not to mix, not to mess up, I use this Z. Yeah, I'm kind of sorry. This is a bit technical thing. I might have to draw and open the paper in order to show exactly what Z is for.
No, that's it's helpful though. Thanks.
Okay, so there are some extra layers for security against some traditional cryptanalytic attacks like differential and linear cryptanalysis, which we call concrete and bricks, in order to the entire structure represent what we call reinforced concrete. So reinforced concrete is basically a material where you have steel bars, inside your concrete in order to provide the necessary durability. So these extra layers, they are rather inexpensive in all situations, but they are needed in order to security. They add a bit like 60% of the gates, but yeah, sort of necessary. And what we have is this sort of a table. So please excuse me for, well, the functions that I didn't participate in the design. They may have a bit of miscalculations here, but I wanted to compare like really apples to apples. So I tried to calculate this number using the same gates with the same arity, like addition is like 3 arity addition, and all table lookups are like lookups of tuples of size 4, something like this. And well, rough estimation of the number of constraints for reinforced concrete is to be like on par with Poseidon Rescue and Pearson hash or similar, so they are all still in the ballpark of a few hundreds. But in terms of performance, they are much better. So we're really happy that they are much better. And depending on the field that is inside, we can be either like 10 times slower than SHA or only 3 times slower than SHA. And I think this 3 times slower than SHA is something that has been achieved by any zk-friendly hash function before. You may wonder what is this field that is so friendly to our design, and this is of course the field when our modular reductions are fast. Yeah, this was, yeah, I think I forgot to insert this slide. So basically, it's the case when in the field, well, all the buckets, almost all the buckets are powers of 2. That's actually not possible for BN or BLS curves, but for certain primes, like close to Mersenne primes, that's possible to have this decomposition into basically buckets of almost all of them are powers of 2, and because of that, model reductions are very fast, and we are only a few times slower than SHA or Blake, and that's why we can now stop being bottleneck implications that are Merkle trees. So yeah, this is all I wanted to talk about the design for the like half an hour, but I can, of course, I think elaborate if there are some more specific questions.
I definitely think it's worth asking them now because Dmitry leaves possibly before the end.
Any questions for Dmitry before we transition over to Plonkup? Luke and I think Josh are going to lead that part. Dmitry, I thought this is great, really interesting work. Obviously, a great result. Definitely looking forward to checking out the paper and seeing some of the other kind of some of the other elements at play here. But overall, really cool result.
Thank you. Okay, let me then stop sharing and let Luca and Joshua continue. Thank you guys for your attention.
Cheers.
Thanks a lot for that, Dmitry. Is the screen visible? Do they even turn the sound on?
Yeah, looks good. I think, yep, your presentation. So we can see the screen and the slides. If that's what you want, then
okay,
good to go.
Yeah, we're good to go. Okay, I definitely think it's worth giving a small high overview. I think most people watching this and people who choose to watch the recorded version will know quite a lot about Plonk and a lot of the snarks and the constructors, because we won't be going through this is how Plonk works and this is how Plookup works. Assume a little bit of understanding the whole snark process and then the particularities about Plonk with its permutation process and whatever. This work commenced between, I guess, what might have actually then been Heliax, and which is now Anoma, and Dusk. And we wanted to integrate lookups into the proving system, but more of like as a custom gate with a selector polynomial added on, and bit dissimilar to other ways of dealing with them, as maybe having them as potentially different proof systems or having them as sub-circuits. And we wanted to kind of marry the two together, because it was alluded to in the paper, and one great example online, the first I looked at Kev's Plookup implementation, that it could go well into the Plonk argument. Sort of several months into that work, Dmitry began to create this, we've begun to implement, but Dmitry started roughly the same time implementing and designing this Plookup-based hashing function, reinforced concrete. But as you'll have seen from like the layers of bars and the things that he described, there is not just lookup gates inside bar. There's also concrete, there's also bricks, and there's also like decomposition functions, so that you need like modular gadgets. So basically for us, we wanted one circuit that could assess all of the different types of gates in one, and ultimately, in the end for use cases, if that hashing is in some kind of contract, some kind of secret key knowledge with ECC gates and stuff, we wanted to kind of merge it all together. And in doing that, Josh and I came across some interesting caveats of merging Plonk and Plookup in sort of the processes. And the resulting protocol that we've implemented and we've gone for, where we called Plonkup. I guess another Plonk-ish based derivative, ultra turbo, everything, using this kind of principles that we'll go through in a second. So the first thing I think, more specific to what I say, it's a method for unifying Plonk and Plookup proving systems. So it takes the advantages of Plonk and some of these universal updatable snarks in general, being succinct and fast and quite small proofs, but we also leverage lookups initially for things like bitwise operations. I think we just wanted to shave down the expense of a logic gate using XORs and things. And because this supports arithmetic gates and lookup gates in the same circuits and others, but specifically those, if you enhance it from vanilla Plonk, it helped to basically be the backbone for building reinforced concrete hash on it. So if you look at the papers and you kind of follow the logic of Plonk, the big P in the acronym, the permutation being sort of permutation equation, product equation, polynomial interpolation, then polynomial satisfiability before doing the verifier. The kind of structure in the final protocol section of the paper is followed not dissimilarly in the Plookup paper, in that they both have the quotient, they both have a linearizer, they're both doing some kind of checks to hold that at points copy constraints hold, and putting them together showed some interesting areas. So Plonkish protocols, as I said, now, and I think the last, if I'm not mistaken, zkStudyClub by Ariel was F for Plonk, which is the super fast verification to load the Ethereum gas. Then Plookup, Plonkup, Halo to Ultra Plonk, which is, I think, a Plookup leverage for awesome custom gates, and Turbo Plonk. The characterization of what sort of brings these together isn't the system of turning a circuit into a set of polynomial equations or some kind of QAP, because that can be generalized for lots of different types of snarks. It's the kind of acronyms on their own, which I really like, almost concatenates perfectly, that we have these permutations and these copy constraints. We have a gate equation, which is dissimilar to R1CS, sort of kind of being known aptly as arithmeticization through Plonk, and you can add on and manipulate and just check satisfiability of all of these gates at a circuit. They're evaluated over some Lagrange basis, so they have in common some subgroup of roots of unity, and you say, oh, well, they share this for some interpolating set of points, and they have a grand product argument. I'll let Joshua explain the next couple of slides on how some of the copy constraints work, and he'll go through his beautifully designed aesthetic example.
Yeah, all of these Plonkish protocols I kind of view in the same way. I view them as a switchboard. And so I do this little switchboard here. What you have in each row is a gate or a constraint. So I've got three types here. I've got addition, multiplication, and lookups. Each row needs to satisfy that gate for its row. But then you'll need some way of connecting these together so that the output of one row can be used as an input for another. And so I kind of imagine plugging wires or cables into these jacks like it's a switchboard. Yeah, can you go forward one?
Yeah.
Luke? Yeah. Here I've got C1 connected to A2, and B4 is connected to A5 with these kind of cables. And these cables are just constraints, equations between variables, but they're kind of special and they're treated a little bit differently than the other constraints forming the rows. These are called copy constraints, and we can use these to build a permutation, and we can check the permutation with a large product. In the Plonk paper is called the grand product argument, and Plookup has its own product that checks something kind of similar. Seeing these permutations, it's kind of natural to imagine we could combine them somehow or treat them in a similar way. Just some terminology on the next slide. Wires, these are columns of the prover's private inputs and the vectors of length n. So on the previous slides, I had A, B, C, and D. Each of those are wires. A gate is a relationship that a row of the prover's private inputs must satisfy. Plonkup supports arithmetic gates and lookup gates, and we can also put custom gates in there as well. And These are sometimes called constraints as well. Selectors are vectors that turn gates on and off. So if you have a 1 at index k, the lookup selector that turns the lookup requirement on for row k. And we have a selector for each kind of gate that we want. If you have addition, multiplication, lookups, or anything else, each type of gate has its own selector, and we can turn those on and off whenever we want. Sometimes selectors can give you an auxiliary value, like you could use one maybe to choose a specific table, possibly, or contribute a scalar into a gate. And we have copy constraints, which I've already talked about a little bit. They are equations that ensure that certain variables take on the same value. And we use them to build a permutation which swaps variables with another. The swap is supposed to preserve the value of the product. And if that does, then you can assume that they're equal. The circuit description is the selectors and the circuit length and the permutation, including the copy constraints. All right, so oh yeah, go ahead, Luke.
The core part of what lookup brings. So if you can imagine, Plonk has its permutation equation, and Plookup has its lookup equation, which kind of does the same checks where you're looking to basically collapse a 3n product term into a term and an n product term, should I say. They do this to provide, I think, what I call as non-native finite field operations. So because these proving systems, the snarks are constructed over finite fields, as Dmitry explained before, some things are very unfriendly. So a lot of the operations done in SHA-3 are unfriendly inside of circuits. When you need to create these gates, convert them to circuits is very slow because they're things like bitwise operations, and they don't work too well over particular finite fields. And often you have to constrain them down to a different modulus that they weren't originally, like in the context of big integer emulation. So Plookup helps with this by basically, you can imagine it out of circuit, creating these tables, somewhere from like 0 to 2 to the n in length. And these tables have pre-processed values, perhaps of an exclusive OR between gates, or in Dmitry's case, some modular prime outputs for some input when you decompose a scalar. And you can pass these to the proving system. And rather than do what Plonk does very nicely, which is take this standard gate equation and extend it such that you can, I don't know, take for example, a normally difficult operation in R1CS, like ECC, and find tricks that you can do with this gate equation. Rather than doing that and extend it, you can just perform one operation to scan an element of this pre-processed table and sort of simply place the output wire as the output you get from this table, and then just include that table for a different part of the proof later. So for our example, we have, we use 4, so we show this with things like compression challenges. We have lookup tables that equal to kind of the number of the wires. So during the creation, and I won't do too much implementation specific of the circuit, when you're building, perhaps even prior to pre-processing the circuit, you are just passing the satisfy the wires 1, 2, 3, and 4, kind of left, right, output, and 4 to the circuit description. And then later on, when creating the proof, as Josh said, these parts where the selector's turned on for that particular gate are kind of taken out and treated as a data structure for what we're going to refer to as a query table. So with the gate equation I was talking about is this particular principle. So if you have some gate in arithmetic turned on, you might know it's a multiplication gate for the QMs turned on, and the L and the R are off, and then the O's on, and depending on constants and fault-wise and public inputs, it changes again. But the kind of augmented side you can see to this, that I think is in the subtext of a lot of like the turbo Plonk program syntax, and a lot of the descriptions on Breitenberg library, and a lot of the descriptions on the DustPlonk library and ArcPlonk, is that you can kind of extend this on, and then it does some fanciful combination with it that provides this custom gate functionality. And for us, and we'll introduce the selector in a second, it's like a lookup gate. So you'll be scanning this set of tables for a certain index I, and you're finding this lookup, and you're taking it out, and then you're treating that as part of the query structure. If any questions, just put them in the chat, by the way, someone can read them out. So what we do this here, and this is where we start to get into the difficulties. In the original Plookup protocol, you define a compression challenge, and this compression challenge is just something randomly generated from the transcript, perhaps some hashing to get some random scalar, and you apply it to all of the columns of T. And what you end up doing with these 4 columns of T for, I don't know, maybe the exclusive OR between 2 numbers plus an addition or something, or whatever operation you've gone for, is you apply this compression challenge and you bring them all the way down to a set of field elements. So the T is a set of field elements. Now, as sort of, you can imagine, as a single column. And the F has the exact same compression challenge done to it for all of those where the valid lookups have been taken and pushed to that side. So the same compression challenge, and F only taking lookups from T, should mean that basically any value which could have existed in T can exist once or more inside of F. And then that's where we got on to dealing with what can be seen now as 2 basically long columns of lookups and queries. And I'll let Josh take this.
Yeah, so here we have Plonk's grand product argument. And if you may have seen this before, and if you kind of know how it works, you probably will help to understand the Plookup argument and our improved version. You have this accumulator, and we accumulate this big product by recursion. We set the first element to 1, and then each element after that we multiply by this big product, and that product contains the prover's wire values, and the index of that value is what is I there, and some random scalars beta and gamma to kind of help separate these values from mixing with one another, or allowing the prover to choose adversarial values. And basically, if every element in the numerator is also found later in the denominator, then when you are finished accumulating all of these up, the final element should be 1. And that should occur at the nth element of this vector. But if we're starting from 0 and you go up to n, and this is really a length n vector, a zn doesn't really exist in this vector. And because we're using these cyclical subgroups, it turns out that the kind of nth element of this vector, after we interpolate into a polynomial, it just wraps around to the beginning and is equal to the first element. So this product argument works as long as Z0 is 1 and the accumulation is checked between every pair of elements. And even when you get to the very end, you try to accumulate kind of past the end of the vector, but it just loops around to the beginning and will equal 1 again. It's a really nice system. It's got this kind of circularity that allows you to check both ends of this accumulation vector at the same time, because it loops around and connects to the beginning. So then Plookup has a kind of similar argument. Yeah, this is essentially what I just said there with this Lagrange basis slide. So then Plookup has a kind of similar argument. What you do is you have the public table T and the prover's list of queries F. In the original argument, the query list is a little shorter than the table by one element. The prover concatenates T and F together and sorts them to create this vector S, which is of length 2n minus 1. Then S is split into two halves, each of length n. So you have the lower n values and the upper n values. And if you think about the fact that S is length 2n minus 1, that means the lower and upper halves have to overlap by one element in the middle. And then we can kind of do this accumulation again. Can you go back one, Luke? We can do this accumulation thing again. If you look at the denominator, we have H1 and H2. Basically, that will run through all of the elements of S. And what we have in the numerator is elements of F and elements of T, the table. If each element of S is found either in the table or the queries, then this whole product will cancel out again, similar to before, and equal 1. The only problem is that this vector is actually shorter than the previous argument. This only goes up to, it only has n minus 1 elements of its own. So it ends one element early. So you have the initial element, which is 1, and the last element, which is also 1. But you can't accumulate past the last element and loop around to the beginning because this vector is shorter. If you try to do that, you'll end up with a garbage check at the end. So unfortunately, because it's one element shorter, you don't get the nice circularity that the previous argument had. And it also means you have to do some extra checks that you didn't have to do with the original Plonk grand product. So here are the checks that you need to do. This first check uses a Lagrange basis polynomial that's L0 of x, which basically means we are just looking at the first element of that vector. So this is saying the first element is 1. The next check says the last element is 1. The big complicated check, which is running off the page, checks the accumulation between elements. It's got this extra factor, the x minus omega inverse. That prevents this check from occurring at the very end because we can't loop around in this version. So you have to include that extra thing. And then there's this overlap check, which checks that the last element of H1 is the same as the first element of H2. So you have these 4 checks. This, we originally implemented this way, but we ran into some issues with it. It's possible to do it this way. It's just, it's a little tricky. And it's not super efficient. Additionally, there's a compression check. This is using F, the query list, and comparing that against the values in the wires. But since F is shorter than the wires, you have to make sure that this check does not occur at the last element. That's why we again have this x minus omega inverse there. So juggling this extra vector that is a little shorter than the rest, we just kept running into issues with that. So,
I think
yeah, go ahead.
I was just going to say, I think the majority of this was covered by what you're saying. So they don't wrap at the beginning and the end. And I think it's important to highlight why the sort of splitting happens. So in our version, we split the differences based on whether their index is odd or even. Whereas when Josh is talking about the concatenation, and that also comes to our sorting process in a few slides, you take these F and these T and you sort of put them together, but you have to sort a new vector, S, which is something with respect to T, such that it's in a particular order, because not dissimilar to, well, almost the same as the previous Plonk arguments, or where you're checking this grand product, you kind of have one that you can imagine in order versus something that's shifted or permuted. In this case, a rotation by one, or whatever you apply to the things going into the numerator of the argument. And concatenating these together just means that all repeat elements are in order. So you'll have all of elements of T going up from 0 to 2 to the n for whatever you produced, and then it's a single list because of the compression. And then with F, you sort of just insert where necessary, and then you split in half down the middle. And then, as Josh said, you're just checking that those two middle elements are the same, but it doesn't work when the vector of F that you were going for is in fact shorter than a lot of the others. So we found a different way to do this, such that we could still have it and mitigate a few of the checks. So you can take this if you want, Josh.
Yeah.
Take the rest.
So we came up with an improved argument. This was Luke's idea, and it solved all the problems we were having with the difficulties with these vectors of different lengths from the original argument. And what we do is we allow the query list to be also of length n. So all the vectors are now length n, all the same length. We concatenate them again into S, which is now of length 2n. And this S also must be sorted. Then we split S into two halves, H1 and H2, each of length n, just as before, except now we split so that the odd indexed elements of S go into H1, the even ones go into H2. So we kind of alternate back and forth between H1 and H2. And we accumulate a product in a vector P by recursion. This looks almost the same as the previous argument, but if you look at the denominator, we've changed the way that the H1 and H2 elements are referenced there. In the left factor, we go from H1 at I to H2 at I, which H2 follows H1. So those are adjacent elements in S. And in the second factor there on the right, we go from H2 to the next element of H1, which are also adjacent. So we're going from H1 to H2, and then to the next one of H1, and so on and so on. So those will still run through all of the elements of S, and should still cancel out with either a query value or a table value. And now we have a vector that is the same length as all the others. And the initial element here is 1. You go through the entire vector accumulating these products up until you reach the end. And then the kind of next element after the end should also be 1 if these all cancel out. But because of this circular cyclical group that we're using to interpolate our polynomials, the kind of element after the last one just loops around to the beginning and becomes the first one. So you can check both the first and last element just with one single check. So this kind of puts things more in line with the original Plonk grand product argument. It still has that circularity and is really nice. So as you can see here, we get rid of a bunch of checks. Now all we need to do is check that the first element is 1, and check the accumulation. The accumulation is also a simpler argument because we don't need to prevent the accumulation check from happening at the end because this fully loops around. So the accumulation between every pair of elements should hold. We don't have to ignore any pieces. So also the compression check is a little simpler as well because now F, the queries, is the same length as all the other wires. So we don't need to prevent certain elements from being checked. We can check them all.
Yeah, we've specifically there removed, if you remember from the previous slide, that omega term.
Yeah.
And to kind of high level, because it must be getting, well, it's getting towards the end, but also an hour and 12 minutes in, so people will be watching. We said that we have this wraparound 1, but in the actual proving system itself, by doing this, we were able to send less evaluations of like the shifted basis of H2. I think we went from 5 to 3 evaluations sent for the H1 and H2 polynomials, which were the split of the S1 and S2, if you remember. This works so long as T has 3 or more distinct elements. That, of course, is a small caveat, but I think the likelihood of you ever generating a table with less than 3 for use is very small, and you can always simply extend for that reason. So maybe that'll be more of an implementation caveat. We mitigated this overlap check, checking the middle elements, and what Josh was referring to before with the kind of loop back around of the end going over the accumulator being 1. We're calling, it's kind of, to me, it's like the head and tail of a coin, or if a snake represented some kind of modular number line. That's how I sort of imagine it. The enabling for these alternative is something now a little bit different. So this is the last and most different part of the polynomial checks, and it's actually the part of concatenation that we come to. So what we found when we first made benchmarks on parts of this proving system is it was quite good. It only distinctly stood above Plonk due to the extra commitments and some of the extra evaluations, but it didn't remain constant. Its time complexity was not the same. We couldn't get the O(n) log n, but the verification was constant. And it was because one of the operations inside was being done in a different time complexity to the rest. And this was the sorting algorithm. So if you remember back to T is compressed and F is compressed, where F was the valid queries, well, the proof will check are the valid, F was the queries, and T was the pre-processed table, and we're compressing and concatenating together upon field elements. On the compression challenge that's applied, these go down to a single column of field elements. So you can't sort them based on their underlying values because there's no modular, you can't, unless you do a modular reduction, you can't see the actual value inside. So you're basically taking elements of F, looking at what the field number is, and then taking elements of T, taking elements of F and scanning T, searching the vector, which is a nightmare. And then whenever you find it, you're sort of inserting it so that you can have that length of repeated elements. So where you have S, which is just like all of the elements together are all the exact same number. It's not randomized. And that was difficult because some of the algorithms we found were n² in complexity. So I think around the 2 to the 17, the proving time was really shooting up. We found a few caveats where we could have done it, I think, and correct me if I'm wrong, Josh, n outside of log n plus n outside of n² or something.
Yeah, something like that.
Someone we're discussing doing it different hash maps. And then we tried to work around this problem, and the thing that came about is on the screen. So it was to add to what we're now calling the mega permutation on top of the Plookup more terms at the end, where we provide a sorted version of the table T with an extra challenge, visual soundness, and we're looking for taking the T, and before we treat it with respect to how it to what it looks like after its field element and inserting F to create this S, we're actually reordering T and we're calling it T prime assorted version, and we are inserting with respect to that such that we get a set of field elements that where you can organize all of the numbers together, and we're able to go down to algorithms which take us to O n log n. This problem is dealt with differently across proving system, as I understand it. Aztec have kind of a different type of circuit and how they do it. The zkStudyClub Halo 2 just takes the whole element, the whole vector, sorry, and does a permutation on them, and it does the lookup arguments as part of the sub-circuit inside of this great Halo 2 constructor. So there are different ways to do it, but we found for us that this is the easiest and most logical way to continue to augment onto the Plonkup. But a question that we leave and remains is can the prover sort S according to T, not T prime, using an O n log n algorithm, and thus we get that consistent time complexity across the whole proving system without needing to add this T prime in. Because what that makes us do is it makes us have extra evaluations to this vector that the verifier must have on the transcript or in the proof, whatever. I believe that's everything for today. Hopefully leaving on a nice question. And if you guys have any questions, then shoot them over. Want to say thanks a lot to Marta, Hector, Jose Luis, and Professor Kevin Moe for helping along with this work and co-authoring some of the literature with us. It's been really fun work with Dusk, Anoma, Ethereum, well, not really actually with Dmitry's work, but Dusk, Anoma, and Polychain. And feel free to check out the implementations, and hopefully we get some of this submitted to a conference soon.
Awesome. Hey, thanks guys. Fantastic presentation. Really appreciate all the time that you guys took to come and present. I think there might be some questions popping up in chat. Nope. Okay, so no questions on the chat. Does anyone in the audience have questions? Particularly, I think there's some folks here who are working on some of the other versions of Plonk that were previously mentioned. It might be kind of interesting to hear their perspective on this construction or questions that they have. So I guess I'll open it up if anyone in the audience wants to ask a question. So with that bait not taken, maybe I'll just ask you guys, can you, oh, wait, there is a question. So I'll let you guys go ahead and take that. If you want to read it aloud and then answer, that would be great.
What is the degree of the mega argument? If I'm not wrong, it's 3n plus 2. Is that correct?
I believe you're right.
Yeah.
There are other checks that have higher degree even than that, so it didn't increase the overall degree at all.
Yeah, this was probably the largest problem running in for us, and always looking for improvements, advice and suggestions on combining. Linearization was easier to do and keep folding it down, but we tried to actually put all of the Plonk terms, so the standard Plonk with the 4 wires and the Plookup, plus the specifically sorted table with the different overlap checks all into one, and the degree of the polynomial blew up, so we couldn't do that. So I think how we do it is we have to distinctly introduce one more polynomial, which we sort of called the lookup polynomial, but it's now become the mega permutation. But yeah. Yes, I do have an idea about where future improvements can be found. I believe.
Sorry, Luke. Make sure can you read the question? So for the purpose.
Sorry, yeah.
Everyone will get to benefit from it.
I admit if I forgot to read the first question, the answer the question was, what is the degree of the mega argument? The one with T prime added. The next question is, do you have any clues about where future improvements could be found? I think dealing with different lengths of lookup tables could be widely advantageous. And I also say, alluding to, I think some people, or I may know some people who are working on it, maybe to get an n over 2, where you can have like the lookup argument not necessarily need to be padded to the length of the table and things like that.
And then I think another question, which I'll just read here, is what size FFTs are you guys using? I think that may be a derivative or a follow-on question of the original question that Kay asked, which was, what is the degree of the mega argument? And then I think you answered, Luke, and I think he meant this to be a follow-on.
Okay. Yeah, I think I'm not exactly sure what you mean, but we do FFTs with I guess radix 4. We've got the FFT for the big quotient polynomial is degree like 4n, 4 times the degree. I don't know if that's what you're asking. Cool.
The question is, are there any places in particular where this system would be more suited, or perhaps a type of computation that it would make proofs much quicker to make? Well, yeah, integrating this kind of as a look, this integrating this lookup as a custom gate, you're just leveraging a wider array of operations, perhaps ones that could be done previously. So to give like an industry, or I guess in a blockchain company, tangible example, previously using Poseidon hash on the libraries we were using before on the Poseidon 252 was 953 gates. But when I implemented it with Errol using Plonkup as the underlying proving system, it came down to sort of 360 gates. It's being improved based on, I just saw Dmitry, I think, has like 265. There needs to be some work done with the representation of modular numbers for that decomposition F box. But if you take that and you replace some of these circuit hashes with reinforced concrete instead of Poseidon, then yeah, we're able to already drop them to the next power of 2. So, half in the proving time. So I think, yeah, that's very useful. The use of integrating lookups is fantastic, and I'm sure ultimately endless. Having CPU instructions for like C instructions for CPUs, having whatever XORs, Sinsimilia, hash function, reinforced concrete. But also, if you look at Polygon Hermes EVM constructor, they're using loads of these circuits loads of these lookups, as inputs to circuits for Ethereum opcodes lookup. So I guess anything that you could take from outside the circuit that is traditionally expensive and brought in and evaluate cheaply could be something like that. I think we're at the stage now where it's just a lot of like plug and play, which is almost exciting. Maybe a question to Dmitry: how much cryptanalysis would reinforced concrete need before you can suggest to use it in production? It's not here, but I would guess that he would say use it straight away. I think the rule of thumb is probably about 25 years, isn't it, for crypto systems? Maybe even longer in some cases.
Yeah, obviously, rule of thumb that's hard to follow in the zero knowledge, practical applied zero knowledge application space, given that all those constructions are new. Awesome. I had a quick question for you guys. Can you zoom back up to the slide where you kind of list the Plonkish constructions? By the way, I love the switchboard metaphor and diagram. I think that's really cool and very helpful. Yeah, I guess maybe pop up one more. The one that lists basically all the recent work.
Okay, yeah.
Great. Yeah. So I was just curious how you guys kind of think about, I think Plonk is becoming a pretty vibrant architecture that a lot of people have used as a basis from which to build kind of their own kind of derivatives of, which you guys are one. I guess, how do you think about where Plonkup sits in the family of these protocols, and are there potential applications or use cases that maybe your construction is particularly well suited for? I know you just mentioned one, but I guess I'm asking the question vis-a-vis, like, for example, comparing Plonkup to Halo 2 or something like that. So I guess in this family of constructions, where do you guys think Plonkup sits?
We can both answer. I think almost unarguably in some cases less complex than Halo 2, but I also think that we're working on a library right now, a few companies for kind of a wider use case of ArcPlonk, which is designed to leverage ArcWorks' ability to plug and play, something between a KZG10 commitment scheme or an IPA or ultimately Fry. But that comes more from the code side. So I think in that, I think Halo 2 by design, having these sort of different sub-circuits is something we didn't go for. We didn't get involved in having lookups and say standard Plonk arithmetic composing together as sub-circuits for one final proof. And we decided to just see if we could add it in sort of traditional way that we were knowing for as a custom gate, and then be able to just have sort of big Plonk circuits and look for quite raw increases in efficiency. I think of these in front, it's somewhere around the Turbo Plonk, Ultra Plonk. In that, I guess Ultra Plonk is, it is Plonk plus Turbo Plonk's custom gates plus lookup gates, making it Ultra, if I understand that correctly. And they will also have a bit of a different construction for integrating these lookups. Perhaps they will separate it. I know they use like a lot of range gates. I don't know if they're necessary, for the big integer emulation. I don't know if that's necessary for if lookups are necessary for that. But I think more towards Turbo Plonk and Ultra Plonk. I think the thing that categorizes these, and if you were to list the companies like Mina, zkStudyClub, Master Labs, is people are taking the aspect of being able to just make permutations and make proofs about them. Some if you can imagine like a circuit is a big matrix, just some small sections of this data and check that it holds across all points with these grand product arguments. And this does the same, but leverages sort of extra terms on that so that we can have lookups.
Cool. I don't know if you have anything to add to that, Josh.
No, I think Luke captured it there.
Cool. And then expanding on that and maybe zooming out one level up, like, how do you guys view Plonk vis-a-vis other universal, and maybe you can say generally Plonk or your construction specifically Plonkup, how do you compare it to kind of other universal proof systems that are out there? I know you mentioned Fractal. I think Fractal was mentioned at some point during this talk. There's obviously Marlin. So I guess what do you guys, how do you think about that?
One of the things, I will let you go as well, second, Josh. One of the things that I like the most about Plonk is how many variations of it as a result of how many people are doing it. As to, for something like specialized range proofs or for low verification time or specific proving, it might not necessarily be the best. I think it's now getting to tailored discussions where people could argue in really a lot of cases it is the best. But because so much work goes into it from so many different companies, it seems logical to heed towards it, to see if it can be augmented and to use it. If one in this space where I think human resources could be arguably relatively constrained, if one's being like Plonk is being used to power ultimate scaling to Ethereum through Aztec on Matter Labs and through Halo 2 for scaling Zcash, I think it'll personally, and feel free to quote me on this in 10 years, I think it will supersede just because of the amount of work going in it from so many different teams. I think it must have the greatest focus and the largest number of people of all of the universal and unupdatable snaps.
It's so flexible and customizable. I mean, there's a reason there's 18 different kinds of Plonk or whatever, and that's also why I put your Plonk here at the end of this slide. It's maybe surprisingly easy to customize for your own purposes. If you have a narrow use case, you might be able to come up with a really customized version of Plonk that could fit that case better than any of the more general versions.
Interesting. Cool. Awesome. Well, thank you guys very much. I know we're a minute over. I guess final alibis. Anybody have questions for Josh and Luke? I think Dmitry might have stepped out, but any final questions for Josh and Luke before we close today? All right. Well, thank you guys very much again for coming and presenting. It was great to have you.
Thank you for having us.
Thank you.
Thanks everyone for listening.